Right. Well, I'm presenting this because I've failed on finding new entropy inequalities. So I want to tell you about a different project that also has to do with entropy in a slightly indirect way, namely with its operational meaning. And in that case, maybe somehow connects to the workshop. So you might interpret this talk as sort of like reevaluating whether or not we actually had an operational meaning for it. Okay, so this is joint work with Alexander Müller-Hammes, who's in Lyon right now, and it was presented at QIP just like last week or the week before. It's on the archive, you find it there, and yeah, let's just get going. All right. You can see it full screen, right? Is all okay? Yes. Okay, perfect. So what is quantum communication, or what is classical communication? We have inputs from sources. We built an encoder. We push through channels, noisy channels. We put a decoder. We retrieve the output. In the classical case, input is classical, output is classical. For this talk, we're still sticking to a classical input. Okay, there are m input bits and n channel users, just to set some terminology. But now I want to make the quantum, the channel and the encoder and the decoder quantum. But I still want to have the input bits classical and the output bits classical. So essentially, we're studying the classical capacity of a quantum channel. Some stuff of what I'm saying can be generalized, but I want to make the setup easy for these 20 minutes and just focus on that paradigm. We know what the capacity is. Here's its definition. We look at the ratio of m to n. We want to have the probability of the input not being equal to the output to be epsilon, and we keep the epsilon fixed, and we take the limit n to infinity, and then we take the epsilon away. That's the definition. We also know roughly a formula. It's like the maximum over input distributions, and I now wrote the whole label information in terms of the mutual information. Maybe just to connect to the previous speakers, and then there's regularization, which is a little bit of a pain. But the exact formula will not matter for this. It's just that there is formulas, and there's also formulas for other capacities. And so, but I want to kind of like talk about the capacity itself. But it's of course beautiful, and that is, I think, why Peppinger called it the laws of information theory, that these information quantities, Shannon entropies, not only in the single party case appear, but also in the sort of case where several letters are involved, right? Or say like X and Y and so on. All right. Right, and in this quantum case, of course, it's a phenomenon entropy. With, you know all about it. So here's a small observation. And the observation is that that actually the assumption of noiseless encoder and decoder is actually unrealistic. So if you talk to anyone who tries to build a quantum computer, they will tell you that in quantum computing, we will not have noiseless qubits. So we'll not have like these huge circuits that actually operate noiselessly. So whereas it's classically satisfied, quantum mechanically, we don't believe we'll have this even in the long term. At least I don't think many people believe that we'll have this in the long term. There are certain reasons for this, for decoherence, etc. Certainly in the near and medium term, we will not have it. Which is if you think about somehow the weight of work that has been going on in this scenario, it's somehow astonishing. Right, so we're playing with a scenario, but somehow the basic paradigm of assumption does seem to the base for the model does not seem to be there from what we expect experimentally. And I'm happy to discuss maybe this more in detail later, also in the breakout room. So what do I mean? Well, when you run a quantum computation, everyone who has interacted with an experimentalist, and if you've tried the IBM machine, I'm sure you will know that once in a while there are errors happening. So one has this discretized error picture. Okay, also in the channel. But think for the talk as the channel as being this very noisy thing, about 10% error, and think of the error of the gate errors, or the gates per like the probability with which a qubit is hit by an error very small, like think of like 10 to the minus 4 or something like that. Now, entirely new problems appear when you think about this scenario. The first question is actually, is quantum communication possible at all? So is maybe all of this capacity business just zero in this scenario? Could be. It's not completely clear a priori. And then maybe more advanced, like if you have an answer that's sort of yes, then you could ask like, oh, but what about the capacity formula? Is it in this gate error parameter? Is it continuous? So that means like, do I actually recover the formulas that we have studied, you know, that we have in Nielsen Schwang's book, but of course in Mark Rilder's book, and a lot of people, you know, here in the audience have written amazing work on that. So this is what I want to talk about in this particular case. Now, you might say, well, I mean, fault-tolerant encoding has existed since the 90s. It's a highly developed field. Surely this problem must be solved. And so let's review what fault-tolerant quantum computing does. It considers a computation, but a quantum computation is actually viewed as the quantum computation of a classical functionality. So you have a classical input. Think of Shor's algorithm. You have a classical input, say a large number, that and you want to output a prime factor of it. Right? So classical input, classical output, and whereas here in our scenario we're actually faced with a different problem. Because the encoders and the decoders, they actually, in contrast to having classical input and output, so the input here is still classical to the encoder, but it's quantum what goes into the channel. Okay, so if you cannot black box the theorems from fault-tolerance somehow. You have to unscrew the boxes and look if you can somehow save it for that scenario. Okay, so yeah, it's not directly clear what to do. So we embarked on this project, and yes, so on the decoder side as well. So the plan for the talk is to talk briefly about error correction, to talk about fault-tolerant quantum computing, the setup, and then what is called the threshold theorem. Then I want to give you a definition of a fault-tolerant quantum capacity. And then I want to give you a threshold theorem for that case. And maybe just in one slide, I will tell you what the steps are. They're reducing to some kind of effective channel in the original scenario, and then to solve that case. Okay, so let's look at that. So what is error correction? So error correction in the very simplest case is that you have a bit, classical bit 0. What you're going to do to protect it against noise is just going to repeat it. Instead of 0, you write 0, 0, 0, and instead of 1, you write 1, 1, 1. And if only one error happens, so say the second bit is flipped, then the 0, 0, 0 will be mapped to 0, 1, 0, and the 1, 1, 1 will be mapped to 1, 0, 1. In this case, the majority decoders, so you just do majority voting on, where there are more zeros than ones, and you will correctly decode that it's a 0, 1. So this is a very nice kind of brief introduction to error correction. Now, Shor made a quantum version of that, which really is just the same, just you have to do it both for the phase and the bit flip. And here is a circuit for it. It sort of like looks a little more complicated. But what I want to point out is that it's not really clear what happens if the gates now in the encoding or decoding have errors. Right. So this is really beautiful in like protecting you against noise that happens. So how do I do this? Let me see if I have a laser pointer here. No. So you see, like I'm encoding this psi into the code, and sort of like before this E happens, the E is like an error map. I have it in the shore, I have it encoded in the shore code. And if then an error happens, like a single error, I can successfully decode to get psi back. But now this will only protect you against static noise. Okay, so like noise, when it's encoded, but it doesn't protect you it doesn't protect the circuit itself from errors. So if there's gates in the encoding happening, for instance, up here in Adamor gate, you see that the error might spread. And so then suddenly the code cannot take care of that anymore. And you will find that you will get an error at the output. So if you want to do fault-tolerant quantum computing, you have to be sensitive to the problem that the actual encoding and decoding shouldn't spread your errors, because otherwise your error correction procedure itself might fail. And this is like a high-powered technology people have developed, and I'm by no means an expert in it. But there's another, this is sort of like an introduction to that subject. There's another observation, which is very important for the talk. It seems very trivial, but it took me a very long time to actually understand. It's that you cannot protect an unprotected qubit, okay? So it's just not possible. So if you're trying, so you have some qubit, and you now want to, you have this idea, like, oh, great, I want to now put it in error correcting code, because then it's protected, right? Then what could happen is, just as you start the encoding procedure into the code, an error could happen. Okay. Or here in my decoding procedure, if I have a qubit in an error correcting code, a logical qubit, like perfectly super protected, if I want to get this out and get the physical qubit, then it might all be great, but in the very last step, it might bang, and then I get an error. Okay, so an unprotected qubit. So when I have decoded, I cannot protect this. And this is, I think, a very, maybe trivial observation of people who know it, but it took me a very long time. Right. So then what do people do in fault-tolerant quantum computing? Well, they take the input. And why is there not a problem in fault-tolerant quantum computing? Well, it's because the assumption is that the classical information, which is the input, that is stable. So there is no error happening. That's actually the assumption. And so what you do is you take this classical input and then you do a repetition code, and it's like protected. Okay, so the assumption is somehow the stability is outsourced to the classical part. Then you encode, then you have this encoded circuit. And then you do your quantum computation, all encoded, and then you decode again. And because the output information is classical and stable, you're all fine. So if errors happen, errors here don't matter to you basically because it's stable. And then if errors happen in here, then there's like special constructions called gadgets and all sorts of stuff. It's amazing that there's done so that the errors don't spread. So the error correction intuitively should correct more errors than it introduces, right? So you're doing error correction the whole time, and you're like correcting more than you introduce, and then overall it goes down. That's the idea. All right. So for the talk, there's different noise models you can have, but it's not so important for us. We're going to think of a very simple noise model, like every position is going to hit by a Pauli error, and say the Pauli error is the IID in the circuit, and just think of like the delta parameter. It really doesn't matter. We can generalize a little bit here and there, but it's sort of like not the gist of the point. Okay, not the gist of the idea. So think of a delta error that's hitting each qubit, and then like a random Pauli is happening. Okay, that would be one way. Or you think you hit the depolarizing channel, completely depolarizing channel with like a delta error happening. Okay, all right. Yeah, I managed the gadgets already. So in order to understand this whole encoding procedure, what you do is you take your circuit, you write it in a universal gate set, and you maybe, people have ingenious constructions there. And then every gate in this thing, if you do this encoding, will be replaced by what is called a gadget. So basically a gate in the encoded thing. And I have 7 wires, so every qubit here will be replaced by 7 qubits for the talk. Why is that? Because it's the 7-qubit Stein code, and it has nice properties, and Gottesman, Aliferis, and Preskel have proved a nice threshold theorem for that. And then you put some error correction on top, and what happens is that, like, your circuit, it will be blown up, and you don't do it like once, you do this concatenated, so you do it like a 7-qubit encoding, and you do it a few more times, and actually the error in the effective circuit later will go down doubly exponentially. So, right. 7-qubit Stein code, here it is. If you keep the short code in mind, life is good, doesn't really matter so much. There are some kind of nice things about these gadgets. So sometimes some gates that are really cool. So if you do some like a bit flip, it's basically just like 7 times the bit flip in the Stein code and things like that. So these are called transversal gates. Yeah, I mentioned already concatenation. So you do this like many times in sequence, and then the encoding gets better. How am I doing for time? Not so good, huh? We started maybe a little late, is that right?
We started a little bit late, yes, no problem.
Okay, you let me know when there are 3 minutes to go.
Right, so I think it's 10:15. You have definitely another 12 minutes.
Okay, fantastic. Okay, so similar for the decoding, there's error correction in decoding. The decoding
Actually, no, sorry. You have, I mean, yeah,
sounded ambitious.
My calculation should be done in 1 minute. So let's say you have another 4 minutes.
Okay, I'm going to speed up. Okay, people have studied this. Here's the threshold theorem, right? The threshold theorem by Aliferis, Gottesman, and Preskel, it says there is a threshold such that you can do this encoding and decoding stuff, what I just told you, and the number of gates will stay roughly the same, and the and if your noise per gate is below the threshold, then actually you can get the correct output with high probability. Okay, so the encoded circuit has the same computation result as the perfect circuit. All right, so this is basically the threshold theorem. So if your gate threshold is low enough, then you can compute. All right. Now there are 2 things I want to tell you. There is the definition of the capacity, fault-tolerant capacity. Okay, so here's the definition. The capacity at 0 noise, well, we know what it is. It's our good old definition. Okay. The supremum was over encoded decode pairs with m input bits, and we have m divided by n, where n is the number of channel users. Now, at the capacity for delta noise is now this setup. Actually, we don't have to have a product structure here for the green part, so you could be more general. It's just my picture that doesn't do that. Is the following. It's just the same formula, okay? The only thing is that the supremum now goes over fault-tolerant codes and encoder and decoder pairs in which you encode them, and the attached like encoding and decoding procedure with these bits. Okay, so really it's just the same. It's just like we bring it together. Okay, that's a delta noise. And so what do we? So here's a very important point. The noise is constant. Delta is a constant, and then we take the block length n to infinity. Okay, so it's the proper like information theoretic setup. If you let the delta decrease, then it's basically trivial. Okay, so delta is constant, and then you let n go to infinity, and then you want to compute the capacity. Here's our threshold theorem. There is a threshold such that if you're below the threshold with your noise, the capacity at delta noise has actually a lower bound with the original capacity, and the term, like the deviation, so it will be a little bit lower. It has to be a little bit lower, but it will not be much lower. It will be lower by a function f of delta, which goes to 0 as delta goes to 0. Okay. So it's basically the best that you can hope for. The F depends on the channel, but I think it matters so much. And the level here depends on N, but that also doesn't do much. It's all in the framework, just as a clarification. So with this, you've seen our main results. The proof has 2 steps. Okay, so first we're going to build some kind of effective channel, such that in this effective channel paradigm, we are in the original channel situation where it's noiseless. Okay, so we reduce it to noiseless case, but then unfortunately the channel it sort of starts to being a little correlated. Okay, but we can actually show it has a similar capacity to the original one. Okay, and then we're home. These are the 2 steps, and I won't bore you with the detail. You can ask me.
Yeah, you have all the time for that anyway, so.
And so with that, I'm done. So thank you very much. I think this is an interesting new paradigm. I think it's relevant also for the theoretical interpretation of it. And actually, experimentally, I think it would be great to see this in action. And I think also there is a broader outlook which has to do with connecting different parts of quantum computers with noisy wires, especially in the superconducting case, as you see here. Okay,
okay, thank you.